So we talked deeply about linearity and linear independence of functions. And here's where we'll put all of that knowledge to good use. So we're expanding on the theory of linear equations. We're still only dealing with linear equations. We're going to be dealing with linear equations primarily for the course. And we're going to focus here on homogeneous equations, okay? And as a reminder, what a homogeneous nth order linear differential equation is it has this form, okay? Where the right hand side is 0, okay? So that's important. That's what homogeneity is in essence, is that basically operating with this differential operator on y gives you 0, okay? And we have an asterisk there to note this equation because we'll be using it especially in the statements of theorems. So remark for this section, we're going to assume that all of these coefficients are continuous. Okay, so we won't keep repeating that over and over again. So just take it as a blanket statement. Unless otherwise noted, all the coefficients will be continuous. And the highest coefficient, the an, is not 0 for every x in the interval. So it's identically not 0. It will not be 0 at any point in the interval unless we note that. Okay, so just take those as blanket assumptions for our discourse. All right, so let's look at this theorem. The superposition principle for homogeneous linear equations. Okay. Let y1, y2, up to yk, be solutions of the homogeneous nth order differential equation, asterisk that you see up here. Okay, so suppose you get k different solutions for this differential equation on an interval I. And of course, we make these assumptions. Then the linear combination that you see here, where ci are constants or parameters, is also a solution on the interval. What does that mean? What's this theorem telling us in essence? It's just saying that you could take a solution, multiply it by a constant, and it's still a solution. Or you could take a solution, add it to another solution, or a constant multiple of another solution, and it's still a solution. It's very critical that we're looking at star, the linear, okay? So perhaps we should emphasize here linear, okay? Even though we cite star here, but linearity is crucial, and we'll see that with the proof. So let's look at the proof. And so let these be solutions for the homogeneous linear nth order linear equation. Asterisk. Well then, by definition of the y sub k sub I, then the linear operator L operating on yi should be 0. That's what it means for it to be a, and you know, you'll recall that L here is basically the same, just the same, you know, same form, but written out in operator notation. Okay, so this is what that linear operator is. Well, if it acts on any of these, it's going to be 0 by definition of a solution. And we're going to let y be this arbitrary sum of constant multiples of these solutions. Well then, L acting on y is L acting on this sum. And then, crucially, linearity comes in here, okay? because the operator is linear, then what you could do is, quote, distribute this L on each term in the sum, and also pull out the constant. That's the definition of linearity that we talked about. And so you get zeros and 0. And that's what it means to be a solution to the homogeneous equation, is that when you operate with L on the function, you get 0. Okay, so Y is a solution of the homogeneous linear equation. So we also have a corollary here. A constant multiple of a solution of a homogeneous linear differential equation is also a solution. And a homogeneous linear differential equation always possesses the trivial solution. Okay, so Y equals 0 is always a solution. And notice here, that if we just choose all C's equal to 0, that's Y equals 0. Okay, so these C are arbitrary constants. And so that's where that second corollary comes from. You just choose all C's equal to 0. All right, let's look at an example. The homogeneous linear differential equation has solutions y1 is equal to x squared and y2 is equal to x squared natural log of x as solutions on from 0 to infinity. Then we could just take constant multiples and sums of these two solutions. So this here is also a solution. Okay, how do you know it's a solution? Just cite that above theorem. And notice something here, okay, about this example. We're looking at the interval non-inclusive of 0, okay? So this open interval from 0 to infinity, but not including 0. And you could take a guess why. It's because, well, we want to stay in the domain of the theorem in the section. And this x cubed is 0 at 0, okay? So we can't rely on the theorem if we set x equals to 0. And so that's why we're only looking at the interval where that an will not equal 0. So let's look at another theorem. Criterion for linearly independent solutions. Let y1, y2, and yn, and here pay attention to that. Okay, it's not k, it's n. And n is a special number, okay, because it's a special integer because we're looking at the nth order differential equation. Okay, so we have n solutions to the homogeneous nth order linear differential equations on an interval n. Okay, so this homogeneous equation that we have above. Then the set of solutions is linearly independent on I. Okay, so those n solutions are linearly independent. And we could review what linear independence means, that we basically, can't write one in terms of constant multiples and sums of the others. If and only if, so we get a if and only if here. Okay? It's not just arbitrary functions, but we get a if and only if the Wronskian of those n solutions is non-zero for every x in the interval. And again, and here it's being emphasized solutions. For solutions to the homogeneous nth order linear differential equation on I, the Wronskian of the solutions is either identically 0 on I or identically non-zero on I. Okay? So you don't have to worry about checking that the Wronskian, as long as you find that the Wronskian is non-zero at some point, well, you're guaranteed that it's non-zero for any point in that interval that you're looking at. Okay? Assuming you respect the remarks of what we talked about before, that an is not equal to 0, all the a's are continuous. You get that, okay? So this is a very important theorem, all right? Let's look at an equation. We have this over here. Again, this should cite concern right away that you have this an equal to 0 at 0, but that's why we restrict and we just look at the interval from 0 to infinity so that we could make sure an is greater than 0. We want to show that they're linearly independent. Well, we take the Wronskian. Okay, now you got to take, taking derivative of this is a little complicated. Taking the derivative of this is a little complicated. Then you got to take the determinant. It turns out to be a beast of an expression. But your life could be much easier because all you have to do is just check one point in the interval. Okay? As long as this works for one point in the interval, you're good by the above theorem over here. So which point do we choose? Well, you get these natural logs. And when is natural log 0? Well, natural log of 1 is 0. And so why don't we just try to simplify the expression by just plugging x equals 1 instead of an arbitrary x. If we do that, you'll get this much simpler matrix, and you could take the determinant of that and get 2, and it's not 0 at x equals 1. And because it's not 0 at x equals 1, it's not 0 for any x between 0 and infinity, non-inclusive of 0. Okay? So that makes our lives much easier. We only have to check one point by the above theorem. So here goes a very important definition, that of the fundamental set of solutions. So any set y1, y2, y3, and again, you want to focus on that n there, of n linearly independent solutions. And how do you check they're linearly independent? You check that the Wronskian is non-zero. So, we check that the Wronskian is non-zero for n solutions to the homogeneous linear nth order differential equation on an interval I is said to be a fundamental set of solutions on the interval. So that's a fundamental set of solutions. So for any nth order, and I keep emphasizing this fact of n, okay? Any nth order linear differential equation with n solutions to the homogeneous nth order linear differential equation that are linearly independent, so their Wronskian would be non-zero at some point in the interval, then you have what's called a fundamental set. Does a fundamental set always exist? Well, we have this theorem here. There exists a fundamental set of solutions for the homogeneous linear nth order differential equation on an interval I. Okay, where this is the asterisk going back to that first equation. So we're guaranteed for the nth order linear homogeneous differential equation that we do have a fundamental set. We could always find n linearly independent solutions to that homogeneous equation. So for second order equation, we could find two functions which will be linearly independent and solutions to the homogeneous. For third order, we could find three functions that will be linearly independent, meaning their Wronskian is non-zero at some point. And they are each independently solutions to the homogeneous nth order linear equation. And why these are important is because they're like the building blocks for all solutions to the homogeneous nth order linear differential equation, as we could see in this theorem right here, which is a major theorem, Okay, and it's like the culmination of all that work that we've been doing. So this is what we were striving for. This theorem here, it's very important, about general solutions to homogeneous equations. Now, what is a general solution? As you'll recall, a general solution is this n parameter family of solutions that you could express any solution as part of, okay? Any solution after fixing the parameters you could get. So it gives you all the solutions in a sense. After fixing the parameters, you will get any particular solution you're interested in. It encompasses all of them. Singular solutions, as you'll recall, were not part of the n parameter family. Okay, so those were solutions that could not be expressed as a n parameter family of solutions. Okay, and when you say that you found a general solution to a differential equation, it's like saying you found all of them. Okay, sure, we might have to fix the parameters for a specific solution, but we found every possible solution. We know we could fix the parameters and get to it. In other words, there aren't any singular solutions, okay? And so this is why this theorem is so important. Now let y1 to, again, focus on that n. So you have n equations. They are the fundamental set, okay, for the nth order homogeneous differential equation that we have above on an interval I. Then the general solution, okay, the solution which encompasses all other solutions once you fix the parameters, is given by this sum, okay, where Ci are arbitrary constants. Every particular solution of an nth order linear homogeneous differential equation may be obtained by fixing these parameters. There are no singular solutions. You're not going to find a solution that you could not somehow fix these parameters, including the trivial solution, y equals 0. You would just set c's, all the c's equal to 0 in that case. Okay? It's important that we have a fundamental set, and it's important that the fundamental set has n linearly independent functions for the nth differential equation, nth order differential equation. So let's look at an example of using this. All right, so we have find the fundamental set in general solution of this differential equation on the entire interval. We check there's, the a sub 2, the highest order coefficient, is 1, so no problems there with the assumptions of this section. And of course 9 is continuous. So we'll talk more about actually how to solve this with the auxiliary equation and on. But for now, just guess at the solution. And you could pretty much guess here that e to the 3x is going to work, The exponential has that property that its derivative is equal to itself, but you get this 9. And so you could pretty much guess that this was going to be the case. We're going to check that they're linearly independent, and they are. Okay, and we've also shown more generally that any two exponentials with different coefficients in the exponent will be linearly independent. And it's equal. The Wronskian is equal to -6, which guarantees that these two are linearly independent. This is a second order differential equation, so n equals 2. And these are two different functions. You got two different functions. They're linearly independent. You got yourself the fundamental set. okay, for a second order. For third order, we would need 3 independent functions, but now this is second order, so we got 2. And we're guaranteed by this theorem above that the general solution is this. Every solution of this differential equation can be written with this form where C1 and C2 may be fixed. And that is really reassuring, that there aren't any singular solutions that are going to pop out at you, okay? So let's look at another example. Find a fundamental set for this differential equation on minus infinity to infinity and discuss the general solution. Well, we could solve this with separable equations. It's a pretty straightforward problem to solve, and if you do that, you will get this one parameter family, okay? It is a fundamental set because you have, one equation is trivially linearly independent, right? For n equals 1, you don't have to even compare multiple functions together. So that's trivial that this will be the a fundamental set. Okay, x to the 4th. But what you want to pay attention to here is that it's not a general. So you might think, okay, well, it's a first order differential equation. So all I need is one function. That's a solution. And so you might, rest your head and fall asleep and say, great, I found all possible solutions. But then this solution pops out. Okay, so if you take y is equal to negative x to the 4th when x is less than 0 and x to the 4th when x is greater than or equal to 0, should be 0 there, then you can check that that is a solution. And it's not captured by this, right? C is one constant. It's not a piecewise constant, right? So a constant is just one number. It's not 1 and negative 1 in some other domain. That would be a variable. So what does that tell us? The fact that this solution exists and it's not part of this one parameter family. It tells us that that's a singular solution. So you get nervous and you wonder what's going on. Maybe it's contradicting this theorem. But it doesn't, because why? Because look at this. A1 of x is equal to x, and it's 0 at x equals 0. Okay? So that's what went wrong. Notice that this function gets split at x equals 0. Okay? So instead of, x to the 4th works. Negative x to the 4th works as part of that one parameter family. But this also works as a solution, and you get that difference happening at x equals 0, where it splits off and becomes negative x to the 4th at x equals 0. Okay? And so that's our problem. And that highlights the importance of those assumptions that we made for this section, that an of x must be non-zero for the entire interval, and that we consider, and that all the a's, the coefficients, must be constant there. Okay, so that we don't get any singular solutions, and we could feel rest assured that once we have a fundamental set, we could get a general solution.